And now we're going to start graphing some polar equations just by identifying some features of the graph like symmetry, intercepts, and things like that. And we'll just kind of look at an example here. I have r squared equals 4 times the sine of 2 theta. Now the first thing I want to do is just kind of get an overview of this graph or the function itself, the equation, like the r squared side, for instance. Square something, it's always positive, right? It doesn't matter if r is negative or positive, whatever it is, the square of it is positive. So just thinking, write this over to the side, just thinking through some things, since r squared is always greater than or equal to 0, of course it could be equal to 0, not just positive. We know that the 4 sine 2 theta must also be equal to that, right? So it's got to be greater than or equal to 0. I can't have a positive on one side and negative on the other side. So both sides have to be greater than or equal to 0. With the sine being positive, right? Obviously, if the 4 is positive, the sine, the other factor has to be positive too. So that means the sine is positive, which means that the angle, if you think about, all students take calculus here, if we look at this diagram, ASTC, the sine is positive in the first and second quadrants. And so I will not have any values where 2 theta, now 2 theta is my angle, not just theta, but 2 theta is the angle. I will not have any values for 2 theta between pi and 2 pi, right? Because the sine cannot be negative. Sine is negative in the third and fourth quadrants. Well, here, this would give me third and fourth quadrant angles, okay? If I were to solve for theta, divide out the 2 on all those parts, it tells me that pi over 2 less than theta is less than or equal to pi, has no points, right? The function is actually undefined there, because if theta is in between pi over 2 and pi, that would make 2 theta between pi and 2 pi, okay? If you follow the logic here. Theta is in the second quadrant, would make 2 theta in the third or fourth quadrant, which makes the sine of that angle negative, which can't happen because r squared is positive, okay, or 0. Can't be negative, okay? So there are no points in those with theta in the second quadrant. Also, let's test for symmetry real quick. Let's see if there's any symmetry to this graph. So if I look for instance, x-axis symmetry, maybe I'll do this vertically. For x-axis symmetry, I would need, I need to replace theta with negative theta. So in the original equation, so I take r squared equals 4 times the sine of 2 times negative theta. Well, of course, that's just negative 2 theta. R squared equals 4 sine of negative 2 theta. And the sine is an odd function, right? If you think about the sine as a graph, it has origin symmetry, which means the sine of a negative angle is equal to the negative sine of that angle, right? That's our symmetry for the sine function. So a negative inside can come out. So r squared equals negative 4 times the sine of 2 theta. Well, we already said the sine of 2 theta has to be positive. 4 has to be positive. You multiply by a negative, that's impossible, right? Because you've got a positive on the left. So positive cannot equal a negative times a positive times a positive. So these two things are not the same. And so it also does not equal the original equation, okay? So there's going to be no x-axis symmetry. All right, if we were to look at y-axis symmetry here, Well, with y-axis symmetry, I would need to replace theta with pi minus theta. So I'd have r squared equals 4 times the sine of 2 times pi minus theta. Now this one I'm going to need a little bit of work on. R squared equals 4 times the sine of 2 pi minus 2 theta. And then I need my sum formula for, the difference formula for the sine. And to get the difference formula for the sine, I'm going to steal that out of the book real quick. It is the sine of the first angle times the cosine of the second angle, sine minus the cosine of the first, times the sine of the second. Now if I go through that formula and simplify, the sine of 2 pi is 0 and the cosine of 2 pi is 1. Just rethinking that. Yep, sine of 2 pi is 0, cosine of 2 pi is 1. Yep, okay. So those two values I know, and of course there's a 4 multiplying that whole thing. So I get r squared equals 4 times, well this whole term drops out, right, if one of the factors is 0, and this becomes negative sine of 2 theta. Of course here I can bring the negative out, I get r squared equals negative 4 times the sine of 2 theta, which of course is not equal to the original function there, okay? So it's not equal to 4 times the sine of 2 theta. So again, there's no y-axis symmetry. Okay, so now we go to the origin, or the pole. Okay, let's see if we have symmetry with respect to the pole. Now again, this one, there are two different ways to do symmetry with respect to the pole. You could either replace r with negative r or theta with pi plus theta. I'm going to go with the r and the negative r. Replace r with negative r. And so I would take negative r squared equals 4 sine of 2 theta. Of course, negative r squared and r squared are exactly the same thing. Right? Negative squared and positive squared are always positive, they're equal. And so this is the same equation that we started out with, okay, after simplifying. And so here we do have, let's say there is origin, or I should say symmetry with respect to the pole. With respect to the pole, okay? Symmetry with respect to the pole. So whatever if I were to plot part of this graph, I can always reflect it across the pole. Okay, so because the sine is positive from, let's see, angles, well, I guess just based upon that, I know I don't have any points from pi over 2 to pi, so maybe I just start plotting out points from 0 to pi over 2, give me first quadrant angles, and see if that gives me enough to know what the graph looks like. So let's say theta equals, let's do a table, theta r table. I input thetas, I output r's. So if I put in a theta of 0, maybe a theta of, I don't know, pi over 6, let's do a 30-degree angle. Pi over 4 and pi over 3. Let's see what happens there. Actually, at these endpoints, I might have a value there at pi over 2. let's not, because that might be 0. That might, the endpoint we might be able to include. I don't want to cut that off just yet. Probably on the other side as well. I might need to go back and rethink how I worked with the endpoints on that. But anyway, let's try pi over 2. It's possible I'm wrong on that. We'll see. We'll evaluate it and see what happens. So if I plug in 0 for theta, I'm looking at 4 times the sine of 0. Well, the sine of 0 is 0, so that's radius of 0. So that gives me a point right at the pole, right? 0 radius. With theta at pi over 6, that's a 30-degree angle. Okay, so here's pi over 6, here's pi over 4, here's pi over 3 is a 60-degree angle. And we'll say pi over 2 is our 90-degree angle. So pi over 6, if I plug that in, we're going to get 4 times the sine of 2 times pi over 6. Now we're going to double each of those angles. Doubling that gives me pi over 3, so it's 4 sine of pi over 3. Now an exact value on this is kind of useless at this point because I need to plot these out, right? I need a decimal value. It's going to give me a radius eventually. So I type in 4 sine of pi divided by 6. No, pi divided by 3. Almost messed that up. And that's approximately 3.464. Now, we're not quite done because that's actually equal to r squared, right? So r squared is actually equal to 3.464, which means that r is the square root, or I should say approximately, because we rounded that, approximately the square root of 3.464. So if I pop that into my calculator here, take the square root of that previous answer, and that gives me about 1.86. Okay, so 1.86 is actually the radius there. And we'll start plotting these points in just a moment. I'll get a few more of these down just so I know how far out we have to go. So I've got that one in. Now let's do the same process with pi over 4. So I want to plug in pi over 4. I'll erase some of this stuff that won't match up. There we go. So if I go plug in pi over 4, it's 2 times pi over 4 is pi over 2. Well, the sine of pi over 2 is 1. So that's not approximate anymore, that's just 4, right? 4 times 1. But again, we're taking the square root of that 4, and that gives us 2. Again, not approximately, it's equal to 2. So we have a radius of 2 for that one, for pi over 4. Now we can go through, do the same thing for pi over 3. So if I plug in pi over 3 there, that's going to be 4 times, well, 2 times pi over 3 is just 2 pi over 3. And if I plop those in, 4 sine of 2 pi divided by 3. That gives me, oh, look at that. Same thing we had before, 3.464. And of course, I know that the square root of that, 3.464, will be approximately 1.86. That's what we had just a moment ago. So that works out. And then let's try that pi over 2 angle. So we go through the same process now with pi over 2. And of course my angle then, 2 times pi over 2 is just pi. The sine of pi is 0. So 0 times 4 is 0. And of course the square root of 0 is 0. So we're going to be at the origin there. Okay. Yeah, back to the origin. So radius of 0. So if I think about how those plot out, I need some concentric circles to get my radius in here. So maybe we go out to 3. I got to go past 2 anyway. So let's go 1, 2, 3. Those are roughly 3 concentric circles a unit apart. And so I want to go 0, 0, that's at the origin. I'm going to go pi over 6, comma 1.86. So I go out 1, almost to 1.9, so right about there, give or take. Then pi over 4, comma 2. So on pi over 4, I actually hit the value of 2. At pi over 3, I get 1.86 again, so it's kind of backing off of that radius of 2. And then at pi over 2, we get 0 again. So if I wanted to plot out, sort of loop that around from 0 out and back to 0 again, I connect them with a smooth curve. I should get something that looks like that. Now it's not too bad. A little bit funny right there. I don't know, it looks like a fan blade or a propeller blade. And now that gives us all the angles from 0 to pi over 2. Now I know that nothing from pi over 2 to pi would be included here, so I don't have to keep going with that. However, I do know that there's going to be symmetry with respect to the pole. And so if I were to plot this in the third quadrant, every point in the first quadrant is going to have a mirror image in the third. And so I could just plot that graph through. Oh, that's a little big. Well, you get the point. It's kind of out there to the bottom left, and it's going to be a mirror image of what we just drew. This shape is kind of a double fan blade or propeller blade. That's what we often call it. It does have a mathematical term. It's called a lemniscate. That's L-E-M-N-I-S-C-A-T-E, if I'm not mistaken. Let me double check that. Spelling L-E-M-N-I-S-C-A-T-E, yep. A lemniscate. And a lemniscate is one of these two-sided propellers. As a general rule, what you might notice is that the value here in front of the sign ends up giving you the square of the maximum radius. And so as a general formula, a lemniscate takes on the form r squared equals a squared sine of 2 theta, where a is the maximum radius. Okay, and again, it's a sort of a two-sided propeller blade. Now that's with the pedals or the propellers in quadrants 1 and 3. If I was to repeat this process with a similar formula, if I wanted r squared equals a squared cosine of 2 theta, then I get a lemniscate that's in quadrants 2 and 4 based on the symmetry you would have there. Okay, so yeah, still you're going to get the origin symmetry on that. And that's because the r and the negative r, when you plug them in and square it, you get the same thing. So, okay, so that gives you an idea then of how you can plot graphs. You look at symmetry, you look at points that may not exist, try to figure out a domain for that function, and then you can just plot out some points using a table of values. And typically we use nice values, but you could use anything, right? I didn't have to use pi over 6, pi over 4, pi over 3, and pi over 2. I could have used anything I wanted. I could have put that in degree mode and done the same thing, and just calculated 10 degrees, 15 degrees, 20 degrees, whatever, and however many points I want. But that gives you an idea of how you can do some of these pretty quickly. There are also in your textbook, and I want to encourage you to go into your book to page 598. There is a table in there that shows you many different types of graphs. You have these lemniscates, that's one of them, but you also have other types of graphs. I'm just going to show you a couple of them real quick. I'm not going to go through all the details of all these graphs because there's a lot of them, and that will take a considerable amount of time, but I want you to sort of scan over that table and recognize some of these formulas. You'll have formulas for circles and lines in there. Actually, that starts on page 597. So page 597 to 598, there is a table of formulas. What I really want to focus on, the lines and the circles, I think, are a little bit easier to work with. But you have these lemniscates, you have some things called cardioids. I-O-I-D, a cardioid, C-A-R-D-I-O-I-D. That's an interesting spelling, right? And they are kind of weird looking graphs. They kind of look like a heart, which I believe is where they get their name from. Cardi, right? Like cardiovascular, cardi means heart. Looks like a heart. Anyway, these cardioids tend to have the equation R equals A plus or minus A, that one shifted down, so it's probably a sine of, what is it, theta? I don't know. Could be a cosine. So cosine is the other one. It's A plus or minus A sine of, or cosine of theta. All right, so I'd have to play around with the graph, but one of them is sort of vertical, and the other one is more horizontal, where the graph kind of loops around. I won't sketch it out over top of that, it'll look messy, but so the cardioid is that shape, looks like a heart shape, and would follow one of these equations depending upon its orientation, rotated 90 degrees or this way. Another one is a lemicon, at least that's how I pronounce it. I don't know if there's a different pronunciation for that. But the way these are spelled, L-I-M-A, and then there's a C with a funny little thing at the bottom. I don't even know what that's called. Anyway, the lemicons. And they kind of look like the cardioids, but they're shifted a little bit. Maybe a little bit different. It's basically a circle with a dimple in it. Sort of, kind of. And so instead of having the same coefficient here on the trig function as you have as a constant, they're different values. And so you'd have something like R equals A plus or minus B sine theta, and R equals A plus or minus B cosine theta. So things that are in that form will form a lemicon, okay? And then again, there are some lemicons that look a little bit different. They have a loop on the inside here. Some of them come to a point and some kind of follow through with another part on the interior. So if I can draw one of these, oh gosh, that's a horrible looking lemicon here. Okay, it looks something like that. Mine's a little lopsided. But anyway, that's a lemicon with an inner loop. And those, basically you have the same formula, but without the inner loop, there's a comparison between the A and B values where B is less than A. So the smaller number is the coefficient, the bigger number is the constant. Where over here, it's the same formulas, but the values are switched around. A is actually less than the B value, and so the larger value is the coefficient of the trig function. So Just a couple things there, and then finally you've got your lemniscate, which I just showed you a graph of. Then you have something called roses. They're kind of like lemniscates with more petals on them. And they have their own formulas as well. Get rid of some of these. So you have the rose with if you have an if you have an odd number of petals, your graph is going to look, it could look kind of like, that's one with 3 petals, roughly like that. And so, it doesn't look real nice. Anyway, that is, the formula would be R equals a sine of 3 theta. So it looks a little bit similar to the lemniscate formula, but different, obviously. It's got the 3 in there, and it doesn't have squared terms that are squared. And basically, if you want an odd number of petals, you have to have, it would be like R equals a sine of n theta, where n is odd. Okay, and then the number of petals matches that coefficient. If you're dealing with an even number of petals, the formula is definitely different. For even petals, let's do that in parentheses, looks a little nicer. Let's do, so that's going to be R equals a sine of 2 theta, or again, it's n theta, and I got to double check on this before I say it out loud. So if you have 2n petals, n is an even number, so it's R equals a sine of n theta. Okay? So when n is even, you end up with 2n petals. It's kind of a weird combination there. It's not the same for odd numbers. With odd numbers, the coefficient on the theta is equal to the number of petals. With even coefficients, you get double that many petals. It's kind of weird, but that's true. And of course, if you have some similar formulas with the cosine as well, and of course that just kind of rotates those around. So I did the sine versions, but there are also cosine ones, again, which kind of rotate those petals in a different orientation. So just some things to think about, and you're going to have some matching problems on my math lab, and there's going to be some also where you have to actually plot the graph of these things. And really, I want you to use that table. I don't want you to have to memorize any of these things. If I give this to you on a test, I would give you the table, or I would allow you to reference back to that table. But the table's really only there to help you get an idea of the shape of the graph. But I also want you to be able to come up with some of these without the table, not by memorizing the formulas, but just by plugging in values and kind of tinkering with things like I did with the lemniscate a little bit ago, earlier in this video.